I think it has started.
Yes, indeed. Yeah. So thank you. So
Okay.
once the session finish, you can just go back there and stop it, and then it does the rest. So
Sure.
everyone enjoy the session, and I'm back on the road.
Bye. Happy journey.
Thank you.
Okay, so hi again, everyone. Nice to meet you again. Again, as I was saying before the recording started, I'm so sorry for missing the last week. I was actually recovering from a fever, and so yeah, I'm fine now. Though. So yeah, so let's continue with elliptic curves and what we were talking last time. So just a brief recall of the content that we discussed last time. So we started with elliptic curve. I described it as an equation. An elliptic curve is basically the set of points that satisfy that equation. And we also discussed the group law on it. Like if you take 2 points, how do you add them? We saw some explicit equations and some explicit computations. And also, I think what I stated last time was that in background, how do we get these equations and group law is essentially Riemann-Roch theorem. And then, yeah, there was some interest in seeing Riemann-Roch theorem, so I thought that it would be good to cover this today. So today's goal is essentially to state Riemann-Roch theorem and then using that derive equation for elliptic curve and also try to view the group law on it using our new tools, Riemann-Roch theorem. So before I start, any questions about anything that we have done so far? Anything that I should repeat again? Just please let me know.
Are we still working over the complex numbers or just in general?
In general, yeah.
Okay, thank you.
Okay, so it looks like there are no questions, so we can start. So let x be an algebraic curve. And I'm trying to keep the exposition not too technical. So when I say algebraic curve, there are, so in some textbooks, you will see this word irreducible and non-singular there. So what these things mean essentially is that if you have an equation for your curve, non-singular basically means that none of the partial derivatives simultaneously vanish. And irreducible essentially means that if you think of these curves as given by polynomials, then those polynomials don't factorize. But it's I think for starting point, it's just think of an equation and the solutions and think of that those points as your algebraic curve. So we have this, and what we need for Riemann-Roch theorem is the concept of divisors. So a divisor is a formal sum that looks like, so we have points and then we have coefficients attached to them, and these points vary over x. But not just any sum, I want this sum to be finite. So these NPs are zero, except finitely many of them. And these are integer combinations. So these NPs or coefficients are integers. And when I say formal sum, it's, so think of it like polynomials. For example, when we say x plus x square, it doesn't really make sense. It doesn't really make sense to say what is this x plus x square. So we think of these So this addition is more like a formal notation. What makes sense is if I give you two polynomials, then how do you add them? So we add them coefficient wise. So similarly here, like if I give you 2 points, p plus q, then p plus q is not necessarily on a general curve. We don't know how to add these two things. But what makes sense, if I know p plus q and I know p minus q, then how do I add them? I add them coefficient wise. So the sum will be 2p plus, yeah, 0. So this is what I mean when I say it's a formal sum. Uh, uh, like an analogous thing to think would be, of course, polynomials here. Now with what I so okay, so let me just write it down clearly what I just described. So given two divisors, we can add them to obtain a new divisor. So how do we add them? Let's say our divisor 1 looks like n1p1 plus n2p2 plus nrpr, and then d2 looks like m1p1 plus m2p2 plus mrpr. Now, there is no guarantee that these two devices are exactly supported on the same points. But if they are not, I can artificially extend this by taking my coefficients to be 0. That's what I mean. So d1 plus d2 is simply how we add polynomials, so coefficient wise. So it's n1 plus m1 p1 plus n2 plus m2 times p2, and then so on. So this, if we take set of all possible divisors with this operation, the set of divisors form an abelian group. Now, just to quickly recall what's a group. So we have a set, which is set of all divisors. We have a binary operation, which in this case is addition, this formal addition. And for to check whether this set forms a group under this operation, we need to check associativity. But associativity will follow given that how we add, it's basically same as polynomials. And on integers, addition is associative. So associativity would just follow from that. And we need to have an identity. Identity in this case would just be zero divisors. Basically, take all the coefficients to be 0. That's our zero divisor. And we also have an additive inverse. So if our D is, like for example, n1 p1 plus n2 p2, basically take negative of all the coefficients, and that will give us 0. So they form an abelian group. And associated to a divisor, there's something called a degree of a divisor. So if our divisor is, let's say, summation np p, then degree is basically, let me give it a name, I from 1 to n. Then degree is basically I sum all the coefficients. So degree is np1 plus np2 plus np. And this is an integer because I'm taking integer combinations. Now I have this huge set of all divisors. Inside this, I have a smaller set of all degree 0 divisors. And this is not just this is a subset by definition, but this is not just a subset. This is also a subgroup. So this is a subgroup inside set of all divisors. To check if something is a subgroup, all we need to check is that whether it is closed under the operation and it contains 0 and inverses. So if I take two degree 0 divisors and if I add them, so let's just go back to how do we add. So we add coefficient wise. So if d1 and d2 are degree 0 divisors, then d1 plus d2 will also be a degree 0 divisors, because sum of coefficients is basically, it can be separated into two parts, sum of coefficients of d1 and sum of coefficients of d2, both are 0. So this is, so the binary operation when restricted to this gives me closure, and 0 is a degree 0 divisor. And if you take a degree 0 divisor and you take its additive inverse, that will also be a degree 0 divisor. So this forms a subgroup. Inside this, I have a special subset which I'll call principal divisors. And what are these things? Let's discuss them. So I had my curve. Suppose R is a rational function on my curve X. So associated to this function, I can define a divisor. And how do I do that? So basically, I collect all the zeros of this function. Let me call them Z1 to ZR. And then I also collect poles of this function. Let me change the name. Let me not use the same R. Let me say it's T or something. Yeah. And let me also collect all the poles of R. Suppose they are P1 to PS. Now, what is this divisor? So this divisor, and then these zeros and poles, I can think of them as points inside my X. So to Z1, I have to attach a coefficient. And what is this coefficient? Basically, order of this zero. So just to give an example, if my function is x square, then 0 is a 0 of order 2. So that's what I mean by order. And then if my function was 1 over x square, then 0 would be a pole of order 2. So that's what I do. I collect all the poles and zeros, and my coefficients are orders of them. So I do that for all the zeros. And then same thing, I do it for poles. But except for poles, it will be a negative integer. So order of R at P1, attach it to P1, and then keep going. Now, what is nice is if I take, so if you count zeros and poles according to multiplicities, so sum of all zeros is equal to sum of all poles with plus and minus. So degree of this divisor.
Sorry, Rugby, I missed something.
Yeah.
Where you define divisor of R, what is this symbol for before Z1? Order?
Yeah, order. So
Order R?
I'm saying, so Z1 is a
Oh, the order of the zero. Oh, okay, and the order of the pole.
And for
Okay.
P1, it's order of the pole, except it will be negative. Yeah.
Okay.
Right.
Thanks.
Yeah. So if you take a function on Riemann surface in general and you try to count zeros and poles according to multiplicities, so they turn out to be equal. So degree of this divisor will be 0, because if we take sum of all the coefficients of z1, that positive will cancel out the negative of poles because they are same. So this is a degree 0 divisor. And a divisor of this form is called a principal divisor. So definition: a principal divisor is a divisor of the form for some rational function R on X. So these principal divisors, they sit inside all degree 0 divisors. But not just that, they are also subgroup. So let me just redraw this box again. So we have these principal divisors. They sit inside this set of all degree 0 divisors. And it's not just a subset, it's also a subgroup. Again, to check subgroup, we need to show that it's, so if I take two principal divisors, if I add them, that should again be a principal divisor. So why this works is, so let's say you have two principal divisors, one is coming from R1 and other is coming from R2. So this would be equivalent to divisor of R1, R2. Oh, before I go further, I should define um, I should define an equivalence. So now that we know what principal divisors are, so these divisors, so we can define an equivalence relation on set of divisors. So I'll say that D1 is equivalent to D2 if and only if we obtain D1 from D2 by adding a principal divisors for some rational function on X. So what this equivalence, and it's easy to show that this is an equivalence relation. So for an equivalence relation, what we need to check is that it's reflexive. So every divisor must be related to itself, but then it is. We can just take the constant function. Um, yeah. If D1 is related to D2, D2 is related to D1 just by the definition. And then yeah, it's also transitive. So this does give you an equivalence relation. What it does is it basically packages divisors according to the degrees. So if D1 is related to D2, then they both have same degrees. Then degree of D1 has to be equal to degree of D2. Because degree is additive, right? Degree of D1 is degree of this divisor D2 plus D. So why this works is because degree of D1 is degree of this divisor D2 plus, but then degree is additive. If you add two divisors, their degrees would add up because it's basically sum of all coefficients. So this is degree of D2 plus degree of this divisor, but this is 0 because it is a rational function. So this is, so equivalent devices have same degree in particular. Right. So these, so what I was saying was these principal divisors. So the set of all principal divisors form a subgroup of set of all degree 0 devices. So closure would essentially follow from saying that if you take two rational functions, let's say r and r prime, and if you try to add them, this is basically divisor of r times r prime. So multiplying two functions would add the multiplicities of their poles and zeros. So, and this is again a principal divisor. So that's why. And then it contains identity, it contains zero. Basically if we take a constant function that has no zeros and no poles, so that will give us the identity. So take a constant non-zero function, uh, non-zero. Let's say let's call that constant lambda. So then divisor of lambda plus divisor of anything is, yeah, it would be equivalent. So essentially, sorry, equal. Yeah. And additive inverses. So we want, so basically taking reciprocal would switch the order of zeros and poles, right? So if we start with a rational function r, then take r prime as 1 over r. And now it's not difficult to show that divisor of r prime plus divisor of r would be 0. Because r prime has zeros at poles of r and it has poles at zeros of r. So the coefficient, the signs would get switched and they would add up to give 0. So yeah. So we have closure, we have identities, we have inverses in the appropriate place, and associativity would just follow from it being subset and everything. So this does give me a subgroup. This will I'll use this slightly later to just to start with the concept of Jacobian and seeing how the addition works. So basically the group law that we saw in last class essentially comes from this addition on group level of this divisor business. Anyway, so let me start uh, on some terminology that we need to state Riemann-Roch theorem. So towards Riemann-Roch theorem, so let D be a divisor on my curve X. Now associated to this, I define a set that I'll call L of D. So what does this set consist of? It consists of 0 and all rational functions on X such that when I take divisor associated to this rational functions R on X, such that when I take this divisor associated to R and I add it to D, this should be bigger than or equal to 0. And what do I mean by this is that when I look at this divisor, D plus divisor of R, all the coefficients should be positive. That's what I mean. So in terms of zeros and poles, D cannot have poles worse than what already R has. So that's another way to think of this. Now this, uh, so here is a proposition. This is not just a set. In fact, LD is a vector space over my field K. And K is the field over which my I'm thinking my curve over, right? So this is that field. And proof, I'll leave it as an exercise. This is a nice thing to think of. How do we add and everything? So before that, I don't think we have discussed vector spaces and what do they mean. So I'll discuss vector spaces and bases because we'll need bases later on. But once we know what vector space is, I think this is not very difficult to show that it's that this set LD forms a vector space over K. So this will be an exercise, but let's just briefly discuss. Let me say aside. Let's just briefly discuss what a vector space is on vector spaces. So good example to keep in mind when we think of vector spaces is think of Rn. So example, think of Rn over R. So, and by Rn I simply mean Cartesian product. So we have all those tuples and we know. So a vector space has two operations on it. So for example, Rn, we can add two elements. So if I give you two tuples that each have n elements, how do we add? We add them coordinate wise, right? That's our addition. And there is another operation. It's called scalar multiplication. So if I take a real number and if I take an element of Rn, how do I multiply them? I just multiply each coordinate with that scalar. So R times x1 and then R times xn. These are the two properties. So vector spaces in general are sets that come with these two properties. You can add any two elements and then you have scalar multiplication. This might remind you of fields that we discussed, because also over fields we had two operations that were going on. We had addition and then we had multiplication. But this is slightly different because I'm not saying that we can multiply any two members of Rn. What I'm saying is if you take a real number, then you can multiply that real number with a vector. So there is slight difference there. So in general, a vector space V over a field F. So vector space always comes with an associated field. Like for example, we can think of Rn over R. So Rn is our vector space and R is our field. So vector space over a field F is a set that is equipped with two operations. So one is addition and the other is scalar multiplication. And let me use a notation for addition. Let me say plus, just to symbolize that we have we have an operation like addition. And for scalar multiplication, I'll just use a dot. Now, what are the properties of this addition? There are some nice things that must be satisfied. So first condition is that if you take this vector space along with this addition, this should be an abelian group. Like we have for Rn, we can add any two vectors, and that operation gives me closure because you add two vectors, you get another vector. This addition is associative just because it's associative over R. And then we have commutative, we have a zero element, and then we have additive inverses. So So under addition, it must form an abelian group. And now there are some properties of scalar multiplication. So, and where do the scalars come from? These scalars come from field. So like for example, in Rn over R, this R is a scalar. It lies in my, it is a real number. So for scalar multiplication, if we take two scalars, let's say C1, C2, and I try to multiply it with a vector, that is same as first multiplying V with C2 and then multiplying it with C1. So C1 and C2 are my scalars, they are my fields. And now what is C1, C2? So C1, C2 is the multiplication that is happening in my field, because remember fields have multiplication. So this C1 times C2 is multiplication in field, whereas this one is scalar multiplication at a time. So C2 times V is scalar multiplication at a time. So I start with V, I multiply it with C2, I get another vector, and then C1 times that vector is again scalar multiplication. So there are, it's hard, it's actually I did say dot, but let me remove it because it's very cumbersome to write dot every time. And especially when there are different operations going on. So yeah, in textbooks, usually you don't see too many notations, but it's understood that these are different operations taking place in different sets. So it's good to keep track of that. So scalar multiplication must have this. This can be seen as some version of associativity because we don't want to keep track of brackets every time we multiply, right? As long as the order is not getting affected. So that's it. And then there is an identity element. So there is always an identity element of f, right? 1. So suppose 1 is the multiplicative identity, then if I take that multiplicative identity and I try to multiply it with any vector, I should get back that vector itself. That's another thing I want. So basically these two things. And then I have, like we had for fields, we had addition and multiplication, and then there was some relation between those two things to make these two operations compatible, and that compatibility is what is called distributivity. So similarly we have here, we have distributive relations, because we have two operations and these two operations must interact in some way. They should be compatible in some way. So if I start with two scalars, I add them, and again this addition is in field. So this is addition in field because fields have addition. If I take C1 plus C2, I multiply it with a vector that is same as first multiplying V with C1, multiplying V with C2, and then adding them. And now this is vector addition. And C1 times V is the scalar multiplication, that is. So this is one. And second is that if you start with two vectors and you multiply it with a scalar, that is same as multiplying V with C and W with C and adding them. And again, this is vector addition. And these C1, C2, C, they are in fields, and V and W are my vectors. Okay, so these are the axioms of vector space. So it's a set along with two operations, and these two operations must satisfy all these properties. So coming back to our divisors, so we start with a divisor, we take this set, basically all the functions that have uh, whose poles are not worse than what D's defines or D constraints. And this is a vector space over K. And this is an exercise because, yeah, how do we add? How do we add and scalar multiply? So that's anyway. So now that we know it's a vector space, every vector space comes with a basis. So basis, again, let's go back to our example. We had Rn over R. So inside these, we have these nice coordinate vectors. So for example, if I take E1 to be 1, 0, 0, if I take E2 to be 0, 1, 0, and similarly, I keep on going and I take this n coordinate vectors, then what is nice is that any vector in Rn, let's say x1, x2, xn, can be written as a linear combination of these AIs. So what it means is this vector x1, x2, xn is nothing but x1 times e1, where x1 times e1 is the scalar multiplication that I'm thinking of because these xi's are real numbers, is x1 times e1 plus x2 times e2 plus xn times en. This is what I'll call a linear combination. So basically, we have a bunch of, so it's a finite sum, first of all. We have a bunch of vectors, and then we multiply it with scalars, and then we add them. And everything turns out to be a vector because we are in our vector space. So a basis, and this is one property, right? That I can write every vector as a linear combination of my EIs. That's one property. So second is that suppose we take any linear combination of these EIs. So suppose C1 times E1 plus C2 times E2 plus Cn times En is 0. So what does this mean? So what is C1 E1 plus C2 E2? What is this vector? This is basically this C1 C2 Cn. Suppose this is 0. And 0 again, 0 in my vector space, right? So this 0 is this 0 tuple, right? So if this vector is 0, that tells me that all the Ci's are 0. So this property has a name. It's called linear independence. In other words, if some combination of my basis vectors is giving me 0, that must mean that all the coefficients that I started with were 0 to begin with. I do not have a non-trivial relation among them. This phenomenon is called linear independence. And this property, that if you take any vector and you can write it as a linear combination of your basis elements, this is what is called spanning. So basis is like, so my vector spaces are huge, right? Rn is a huge set. It has a lot of vectors. But I don't have to keep track of all of them. I can go there. I can approach this via these finitely many vectors. So this is the concept of basis. So basis is essentially a finite or maybe infinite. It's a subset of your vector space such that you can write every vector as a linear combination, and those elements are also linearly independent. They do not have any non-trivial relation among them. So that's what, so every vector space has a basis, right? So this is a non-trivial theorem that every vector space has a basis. I don't want to prove this right now because it needs a bit of set theory and Zorn's lemma and everything. But I think we can assume this and move forward. Like every vector space has a basis. So our vector space L of D must also have a basis. Has a basis. And size of that basis is what we call dimension. So dimension of L of D, let me denote it by, let me give it a name. Let me say that that's L of D. I think this is a pretty standard notation in all the textbooks, so this works. So every vector space has a basis, and size of that basis is what is called a dimension, right? And that's what I call small L of D. Like for example, if we go to Rn over R, so this set of EIs forms a basis, right? And there are n elements. So Rn has dimension n over R. Anyway, so now that we have this, oh, there is another. So last, I think last definition before we state Riemann-Roch is this concept of differentials. Or rather, not even differential. It's canonical divisor. So canonical divisor is a divisor of that looks like divisor of, I'm thinking of a good name because I already used lambda. Let me say omega. Is of the form divisor of omega. Where what is omega? Omega is a non-zero differential on X. Now, what's a differential on X? There is a more technical definition of this, like one can define it as a set of module over a ring, but then it's more helpful to see examples. For example, suppose I have a function uh, of X and Y, let's say, or more variables. So a differential is an expression of this form. So we take partial derivative with respect to X in the usual sense, what we do, times dx plus del f by del y times dy. So my differentials are elements of these types. So these are differentials. And any linear combination of them is again a differential. So you can think of these differentials as a vector space and these dxi's as the basis elements that generates them. So this is a differential. And another thing is that if we take any two differentials, their divisors are equivalent. So, e- so you might say this word the canonical divisor, where this identification is going. Any two divisors of this form, if they come from differential, they are equivalent. Equivalence in the sense that we discussed before, that it's related by a principal divisor. Anyway, so now Riemann-Roch theorem. It states that if we have any divisor D on X, the following formula holds. So what's the formula? So if we take L of D, which was dimension of L of D, space associated to D, this dimension is degree of D minus G where G is the genus of my curve. And I have not defined this yet, but let's hold that for a second. It's a positive number, plus 1. Now this formula, yeah, and then there is a correction factor. And this correction factor is dimension of this divisor. And what is the divisor? Divisor of omega minus d, where this omega is any canonical divisor of our choice. That's the Riemann-Roch formula. Yeah, as I said, I have not defined genus yet. One way to define genus is if we think of our curves, and then again, there is this non-trivial reserve that you can think of them as Riemann surfaces. So basically, there are certain copies of, there are certain like donuts glued together. And number of holes or number of handles is basically that genus. So for example, if you think of projective plane or projective line, it's just a sphere. So there are no holes in there, right? So that has genus 0. If you think of elliptic curve is essentially a donut. So it has one handle or one hole. So that's genus 1. Genus 2 would be like two donuts glued together side by side. So that's, and similarly. So that's one way to think of genus. It's in a sort of complex way. But okay, let me just say how do we yeah. So just as a remark, how do we define genus? So there is another way to define genus if we don't want to think of these torus and handles and glues way. It's purely in terms of divisor. So let me open a new page. So what happens is, so this is Riemann's theorem. Given a curve x, there exists an integer such that the following inequality holds. So L of D is bigger than degree of D plus 1 minus G for all divisors. Are there, oh, there was a question. So the question is, are there hyperbolic curves? If yes, then why aren't they perhaps as significant in cryptography? Oh, you're thinking of analogy between elliptic and hyperbolic curves. I haven't heard, to be honest, I haven't heard this phrase before, hyperbolic curves. I don't know what they are. See, the reason elliptic curves are called elliptic curves, like when we discuss, there is, even in the geometry, there is much less of an ellipse thing going on. It's more of how they came into picture. So if you start with an ellipse, right? Let's say you have an ellipse. Let me, yeah. And suppose we take a small segment of it. Let's say this one. And suppose you want to find out what is length of this arc. So it turns out you have to write down an integral to compute this arc length. And these integrals gave rise to elliptic curves. So I think that's where the name comes from, because if you try to study arc length of an ellipse, you land up into integrals and then they generate functions which satisfy the equation that we saw. So that's, I think that's where the name comes from, as far as my, yeah, as far as I know. But
If I could make a quick comment,
yeah,
the torus genus 1 surface can be thought of as rectangles glued together in a certain way. On a higher genus, you can't do it with rectangles. You need larger polygons. And if you unwrap the torus, you get a tiling of the plane into rectangles. but you can't do that with the higher genus surface, but you can do it in the hyperbolic plane. So in that sense, a higher genus surface could be called hyperbolic.
Oh, oh, that's quite interesting. How do we do that again? I mean, is there
It's if you find the canonical pieces, it's easy to
oh,
describe on a
okay,
donut how you turn a rectangle into a donut.
right. I know how to get a donut from a rectangle. So basically,
Yeah,
we take a rectangle, we identify the two sides, like we do
yeah.
one overlap and then another. Oh, I see. Okay, okay, yeah.
But with higher, and you can also tile a sphere in a few ways. But when you try to tile a higher genus curve, it turns out it maps to the hyperbolic plane, not to the flat plane or to the sphere. So
Right.
just that's from the geometric point of view. I don't know if that's helpful.
Okay. Nice. Okay. So right. So Riemann's theorem is essentially that if you start with a curve, then there always exists an integer such that this inequality holds. So L of t is bigger than, so dimension of that vector space is bigger than or equal to degree d plus 1 minus d for all divisors d on x. Now this just depends on x because this is for all the divisors. So this doesn't depend on any divisor. So if it holds for some g, okay, so and let me say gx. Oh no, let me just say g. Okay. So suppose I take a number, say g prime that is bigger than g, for which this inequality holds, right? Then what do I have? That minus g prime would be less than minus of g, right? And then degree d plus 1 minus g prime would still be less than degree d plus 1 minus c. And this, so LD is bigger than this. So LD is obviously bigger than this one also. So if G satisfies this inequality, then every number bigger than G also satisfies this inequality. So the smallest such number, the smallest such G is called G. And this is what is called an arithmetic, oh sorry, geometric uh, definition of a genus. There is another way to define genus in terms of Hilbert polynomials, but I don't want to discuss that right now. Um, that's called arithmetic genus. I'll just mention that here quickly. Arithmetic genus. It's via Hilbert polynomials. I mean, the only reason I don't want to do this here because talking about Hilbert polynomials need a bit of background in algebra, especially like exact sequences and stuff, and that will take some time. It's basically like a zero of a polynomial. It comes from that via Hilbert polynomials. Now what is nice is that for a curve these two things are equal. So geometric genus is same as arithmetic genus, and we are happy with that because I really don't want to talk about surfaces because yeah, my knowledge is very limited. um right, so curves are nice in that sense. So that genus, yeah, this is using divisors we can define genus like this. Now this Riemann-Roch theorem, this is basically an equation, and when I saw this for the first time it really baffled me. I had no idea what was going on and everything. What I found really useful was when I saw applications of Riemann-Roch. So when when we start using this is when it really makes sense, and it starts, yeah, it starts to spike in interest. So let me just restate that formula again here for convenience. So this is Riemann Roch, so RR for short. So L of D is degree of D minus G plus 1 plus L of that divisor of canonical minus D. Now let's see some useful corollaries of this formula, or some useful applications or corollaries, whatever. Corollary because it's a theorem. So suppose we take D to be 0. So set D to be 0. The 0 divisor, 0 coefficient, everything. So what is L of 0? So everything consists of 0. And then all the rational functions are such that divisor of R plus D is bigger than or equal to 0. But then D is already 0. So it's same as saying the divisor is positive. Now these are rational functions, right? If I take a rational function and if the associated divisor, all the coefficients are positive, what it means is that there are no poles. And if there are no poles, there can be no zeros also. So this R has to be a non-zero constant, right? So this just consists of 0 and all the non-zero constants, which are basically the non-zero field members. This is just K. So the dimension of this vector space, and remember these are vector space over K. So dimension of any field over itself is just 1. Because it is the basis consists of a single element, simply the multiplicative identity. You take multiples of that, you will get everything. So in our formula, so L of 0 is 1. So this is small L of 0. So 1, and now let's go back. So degree of D, well, D is 0, so degree of D is 0. 1 minus G plus 1. Sorry, 0 minus G plus 1. Plus L of this canonical divisor minus D. Well, D is just 0, so we don't have that thing. So small l of this canonical divisor is simply G. That's the genus. Another useful corollary. Useful because when we try to derive equation for elliptic curve, this formula will be really useful. So suppose I take my D to be this canonical divisor itself. Now again, let's go to our formula. So we have L of D, but we already know what is L of D. That's just G from 1. Right? That is equal to degree of D minus G plus 1 plus L of divisor of omega minus D. But D is same as divisor of omega. So I'll simply have L of 0. But I know what is L of 0. L of 0 is 1. So I have this equal to degree of D minus G plus 2. So that tells me that degree of canonical divisor is 2G minus 2. So now in the final uh, 5 or so minutes, let's try to derive an equation for elliptic curve. So how do we get equation for elliptic curve? So before even that, like the way I defined elliptic curve was using equation, but now I'm trying to derive. So there should be another definition for elliptic curve, right? So let me redefine my elliptic curve as follows. It is a non-singular projective curve of genus 1 with a point defined over base field. So it's a genus 1 curve with a point. It comes. Now let me try to apply my Riemann rock. So suppose, let's give it a name. E is genus 1 and it has a point, let's say P on E. So now let's look at, so I can look at these divisors, right? P and then 2P. And when I say 2P, I don't mean in the sense of group law because it's just a curve at this point, right? So think of it like a divisor. Oh, no worries, Dimitri. I think I'm exceeding my time, but I should be done in 3 or 4 minutes anyway. So yeah, when I say 2P, think of it as a divisor, and 3P and so on. I can think of these NPs, right? Take those divisors and let's say what is dimension of their associated vector space. So again, let's go back to Riemann rock, and this tells me that this is basically equal to degree d minus g, but g is just 1, so that will cancel out. So degree d plus this dimension, right? So degree d, so this is equal to degree of np, which is just n, plus L of divisor, canonical divisor, minus t. Now let's look at this extra term for a second. My canonical divisor, what is the degree of my canonical divisor? It's 2g minus 2, right? But g is 1, so that is just 0. So this is 0. And then, so what is the, so let me write it. So what is the associated space of divisor omega minus t? What is this? It consists of 0 and then all those functions such that divisor of r plus this one, divisor of omega minus d, should be bigger than or equal to 0. But then let's take a look at degrees on both the sides, right? Divisor r has degree 0. This divisor of omega has degree 0 because I am in genus 1 situation. So now this degree d, but then what is degree of d? Degree of d is n, it's positive, right? So minus n is bigger than or equal to 0. So it's not possible for me to achieve this equality, right? So this is simply 0. So this vector space just consists of 0, right? And basis for this space is just empty set. So this dimension is 0. So if I take these dimensions of these divisors, it just turns out to be. Now let's try to play with it. So I start with, so let me open a new page. So I start with L of P. That is simply 1, right? So that means that basis for LP is simply 1 because it's one dimensional. Let's go to 2P. Now it's two dimensional. So its basis consists of 1 and another function. Let's give it a name. Let's call it x. Now let's look at x again closely. So where does x lie? X lies in that L of 2P, right? But what is L of 2P? L of 2P consists of 0 and it consists of all those functions such that when I take divisor of r and when I add it to 2P, it should be bigger than or equal to 0. But then what does that tell me about this divisor of r? Well, just rearranging terms, obviously this is bigger than or equal to minus 2. But then what does that tell me about the poles? It tells me that I should have exactly one pole at P of order 2, and then everything else should be a 0, essentially, right? So X, oh, uh, just like when I say a divisor is bigger than or equal to another divisor, I basically mean that we look at the coefficients and the coefficients must be bigger than or equal the coefficients of corresponding. So this function X that I had, this has a pole at this point P, which is a fixed point of order 2, and 0 everywhere else, right? Now, similarly, let's go back to L of 3P. Now, this is three-dimensional. So, bases consist of three. I already have one and X, right? So, I need to have an additional element, Y. And now, what is Y? Y is that member that has a pole at P, sorry, of order 3, right? I need that number that has pole of exact order because X has pole of order 2, so it doesn't cut it for me, right? So I have three elements. Now let's go back to 4P. Again, this has bases of four elements, 1, X, Y, and I need a number that has pole of order 4. But I can take X square. X square works, right? Because X had pole of order 2. So X square will have pole of order 4. I'm simply squaring it. So I've got my four elements. Now let's take 5P. So again, I have 1, X, Y, and X square. And now I want a member that has pole of order 5. So we had X that has pole of order 2. We had Y that is pole of order 3. Let's multiply them. That will have pole of order 5, right? Now L of 6P turns out to be interesting because I need 6 members, right? I already have 5. 1, X, Y, X square, X, Y. And now I need one additional member that has pole of order 6. But there are two candidates, right? So X cube and Y square both have pole of order 6. Both are candidates. But now I already have a set of 7 members. I don't need more than 6, right? So there must be a relation between them. So this set, let me say the set because this is rather ambiguous. So the set 1x y x square xy x cube y square is dependent. It means there is a relation between them, right? And basically by adjusting coefficients, I can assume that y square and x cube are the coefficient is 1. So I'll get y square plus a5 xy. And I'm calling this a5 because of the order of the pole, right? Just to keep track of that. Plus a cube y must be equal to x cube plus a4 x square plus a2 x plus a0. This is a cubic equation for an elliptic curve that one usually starts reading with. And now, by change of coordinates, or by basically by, let me say, change of variables, like simplifying this and applying transformation, we can simplify the above equation to y square equal to x cube plus ax plus b. And this is what we call Weierstrass form of an elliptic curve. So, and I think this is what we started with last time, that if we have an equation of this type, It's equivalent. So there are two ways to define elliptic curves. If you start with the definition that it's a non-singular projective curve of genus 1, then you can derive this equation using Riemann-Roch. And if you simply start with this equation, it's not difficult to show that it is a with this condition, of course, that non-singular and everything, that the I'm so sorry, that the associated discriminant is non-zero, which I think is 4a cubed plus 27b squared. So if we start with this, we can show it's non-singular projective because it sits inside projective plane, and it is of genus 1 because it's degree 3, right? So genus has that formula uh, that comes. So right, so these two things are basically equivalent. So what last time we saw was that it has a, if we take any 2 points, then we can add them. We saw equations and we also saw some explicit computations. So what I also wanted to discuss was that how we can see the group law in terms of divisors only. But I think I don't have time. I think it's good if I do it next week. I can also recall some of the stuff that we did, and then yeah, we'll continue with some more cryptographic techniques next week. So, yeah, that's it. Let me end. Yeah, if there are any questions, then I think we can discuss.
Thank you, Rakvi.
Yeah, of
That's
course.
helpful, but it's a lot to digest.
It is a lot to digest. I mean, I tried.
Mm.
I tried to keep my exposition very less technical. So I try to use as less
Mm.
terminology as possible. But yeah, I agree. It's like when I saw this formula for the first time, even I was like, I still don't remember it. I still have to, yeah, I still have to refer to textbooks whenever I want to use this. But it's,
That makes me feel a little better.
but yeah, it's I don't know. The Riemann-Roch theorem on an abstract level still doesn't make any sense to me. It's only that when I saw some applications, that's when it all started to click. Like, why do we use this
Yeah.
sort of stuff? But yeah.
I think I understand the Riemann theorem over the complex plane. It's this generalization that's a little hard to grasp.
Yeah, it's yeah, if we see everything in terms of divisors and groups and just algebra, then it's easier to generalize. But then the downside is it's too abstract and it's too yeah.
Yeah, so I think what I need to do is go over all of these definitions: divisor, zero divisor, principal divisor, and canonical divisor before I can then see how they come together.
Oh, there is a very nice reference for this. So obviously Hartshorne is one book, but I guess Hartshorne even uses more terminology than this. But
I never made it past first page of Hartshorne, sorry.
so yeah, Hartshorne is what everyone recommends. I'm forgetting the title. I think it's algebraic geometry or something. I'll recommend another book that I really liked for first reading. It's I think it's Algebraic Curves by Fulton. I really like this second book. I really recommend it. It's very nice to read. It's very easy to read.
Oh,
It's
thank you.
like a storybook almost. It
Yeah,
also
that's
it's
what we
quite,
need.
yeah, it's quite elementary in the sense it starts with projective planes, projective spaces, everything
Okay.
basic, and then it ends at Riemann-Roch. So Riemann-Roch is like the last chapter of this, and explains everything in detail, terminology. So it's quite nice to read. Yeah.
Thank you so much. That's very helpful.
No worries, no worries.
Yeah, because I looked at the reference you gave on cryptography using elliptic curves, and it doesn't go into these abstractions. It
Yeah,
dives right
no,
in.
it doesn't. Right. it uses very less technical jargon. It's I think it's aimed at the audience which have some knowledge of elliptic curves, but they are more interested in cryptographic
Yeah.
side of it. So it discusses cryptographic like implementations in more detail,
Yeah.
which I don't really find interesting, because it, like, if you take that book, each chapter starts with something mathematical, and then it goes into like bit length and implementing that, and
Yeah.
like
Very, very computational. Yeah.
very computational, which I don't really have a feel for it, because I haven't thought about these things like implementation issues. So I still don't have a very good feel for it and why I should care about it. But yeah, it's really good. Yeah.
Yeah. I mean, for cryptography, I think you need both points of view, and it's hard to bring them together.
Yes, I agree.
But thank you. If I could make one suggestion, would be just to slow down a little.
Okay. Okay. Yeah. Okay. I'll keep that in mind from next time.
And I'll try to hold a study session tomorrow and maybe work a little on the couple of exercises you gave just to show these things.
Yeah, that would be really helpful actually. Yeah. Let me know if I can help it in some way.
Okay, thank you.
Yeah, slow. Even I want to, but the thing is, this 1 hour constraint is, it's, I I don't want to overshot my time also, so I
Right.
try to keep track of two things. But yeah.
Yeah, that's why I'm thinking, slow down and split it into smaller hour-long pieces.
Okay. Yeah, that can be helpful. Sure.
If you think of it in terms of slides, if you write it out ahead of time, or even index cards, then how much fits on a slide takes so many minutes, and you can decide what fits into an hour. Hope that's helpful.
Sure. Sure. Yeah, that would be helpful.
But anyway, thank you very much for your patience in going over this.
No worries. Yeah, yeah. No, it was good for me also to revise this. It's always good. Yeah. I'll just stop recording, I guess.
Looks like it's just you and I have to go myself. Thank you.
Yeah, even I have to